Sometimes people talk of dark field electron microscopy. So dark field electron microscopy is done for the features that which are not visible in the bright field microscopy. And if you look into the moon with a telescope when it is half, when the moon is half illuminated, and you look in the telescope, you will see many features, not because of the dark, but that bright portion will illuminate the darker region. The bright portion of the moon illuminate the darker region, and you will easily see the mountains on the moon. But if it is full bright, you don't see it. And in the transmission electron microscopy, what you do, that the beams are coming, the transmitted beams are coming like this, and the diffracted beams are coming, for example, like this and like this. And you select here and include an aperture to exclude all these. And the brightness of them falls upon that area because there is no transmission there. And with the help of the bright region, you see the darker region. And it gives you a control level of illumination to see the features invisible or inaccessible during the bright field electron imaging. Filament centering. A gun horizontal, gun tilt. So you have a complete assembly near the gun to center it. Because if the gun is not centered, you are talking of nanometer scale tip. And if that nanometer size tip is slightly out of focus, then you don't see anything. So focusing and centering of the electron gun, if you don't have, for example, this cloth, it is the emission source, and it is supposed to be like this. The electromagnetic system is designed in such a way that if it is like this in the electron microscope, it will give you proper number of the electrons required to go down. So if this cloth is like this, or it is like this, or a little bit like this, then you are not getting that information. And what you are focusing, when your source of light is not under your control, how can you control the beam from there? So the machine is made for specific condition, for specific orientation, for specific focusing from A to Z, from the electron gun to the screen. And the first thing the electron microscopists do is to focus the gun. And that is why learning electron microscopy needs ears, right? In the modern world, people are going for shortcuts, but in the days I was doing electron microscopy, it took me 1 year to become an approved user of the lowest level conventional electron microscope. And that 1 year means at least 8 hours per week. So I used to have 2 sessions, 4 hours. And in the whole year, when I worked, then I was made approved user of the lowest level conventional electron microscope, which was mostly for training purposes. Right? So this takes this time, because when you are moving towards perfection and you are playing with angstrom and nanometer scale features in materials, you must be very, very careful and responsible. When you limit the rays and look towards a bulb, a minor fibers appear in the beam of light. If that fiber is on the sample holder of the electron microscope and it enters the machine, then the vacuum will be destroyed and the machine will stop working. And you will have to start from the start again. Right? So when you are being authorized to work in such sensitive labs, you must be extraordinary in your care and your intelligence and your smartness that nothing is damaged. The price of the microscope you have here, it is depending upon the age of the microscope, it is from 50 million rupees to 100 million rupees. And these are the common microscopes, they are not any specialized microscopes. When I was studying in Cambridge, a room was being built for a microscope and it costed more than 1 million pounds. The room for the microscope. Right? So the environment in which the microscope is placed, it also counts towards the quality of the machine. That if it is in such an environment that there is no stability of the field around, the current is passing in a wire there, but it is enough for the electron to disrupt its path. Electron is a very fine thing. Mass-wise and charge-wise, it is a very small thing, and that affects your result on the machine. So the first thing when it comes to focusing is the focusing of electron gun, and it's tilting, it's translating. You can translate it this way, tilt, so that it is completely in focus. If it is not, then you can't focus optimally the remaining machine. Your start is wrong. So that wrongness will go along up to the end. And many people do it, they just take the, put the sample in the machine, take quick pictures, but they are not scientific. Scientifically, everything must be 100% focused. And then when you get a result, that will be, because you are talking in terms of 0.1, 0.2, 0.3 angstroms. And that accuracy is only and only achievable when the machine is performing optimally. If the machine is not performing optimally, then you can't do that. Single-oriented crystals of tungsten etched to a fine tip. Etching. Here, etching means that you thin down the tip of the electron gun chemically. Because when you move the tip in the chemicals which corrode the surface, which dissolve the surface, you are left with a fine tip. Etching is done chemically as well as thermally. People do it. The three types of samples are prepared for microscopy: cross sections, that you cut the material and look into that cut surface so you can see that what is in between and what are the grains or crystals inside it. The etching, the chemical etching, when the sample is a mixture of crystalline material and glassy material, usually. When I'm talking to you, this means I'm telling you the conventional things. Specifically, you may have many different things, but I am telling you the simplest ones. That if a material contains crystals in a glass, embedded in a glass, then one phase will be softer and the other will be harder. When you expose it to the chemical, for example, hydrofluoric acid or sulfuric acid or whichever chemical dissolve that particular phase, then you will see the harder phase left and the softer phase removed. And that will give you the exact morphology of the inner grains or crystals inside the material. Thermal etching, when you have a sample like this. So you look into this sample in the optical or scanning electron microscope, you will see no features inside it. But if it has been sintered, sintered means optimally densified at 1500 degrees Celsius, then polish this sample finely and take 10% of this temperature out. When 10% is removed, it will become 1350. How much is it? 10%? 150. 150. Right? 150 is 10%. Then subtract 150 from 1500, it will be 1350, right? So heat this material at 1350 for 10 minutes. And what will happen? It will a little bit ease up the grains. And that easing up of the grains means that it will appear like this. That if the grains are like this, so what happened here? Etching relaxes the microstructure of the material. If things are solidly bound together and you heat them, they relax a little bit. And that relaxation is basically etching. In the chemical etching, you removed the softer phase and left the harder phase. In thermal etching, you relax the structure and the grains appear like that. Just like you have a pond of water and it dries under the sun and you see cracks there. So the tightly bound regions remain bound and the poorly connected region will relax a little bit. And that is the procedure for 100% crystalline material when there is no glass or sulfur phase there. In that case, the chemical etching is done to finely thin down the tip of the material for that particular purpose. The emission of electrons that are stripped from parent atoms by a high electric field, and a field emission gun tip can be cold or thermally assisted to help overcome the work function, but ultimately it is a high voltage field of 3 keV that is needed. So in the thermo-ionic emission, you heat the filament to give you the electrons. And those electrons will not be stress-free because they have come out because of heat. And when something comes out because of heat, they will be very scattered. Very scattered. Here in thermo-ionic emission, you are pulling electron. You are pulling electrons out of the material to a specific point. Your field is adjusted such that the electrons are coming out and they are collected at a certain point. So you make a pool of electrons under the tip. And then you, through the potential difference, bring it down to the column of the electron microscope. Now, somebody is dropping water and you are collecting them and taking somewhere. And in another case, there is a pond of water and you collect water from there and take it somewhere. The pouring water will be scattered, right? For example, the rain is coming and you are collecting water and taking somewhere. So in the case of thermo-ionic emitter, the electrons are not under control. Wherever the heat reaches, the electrons are emitted from different parts of the filament. But in the thermo field emission, the field brings electron into a stable position. There is no accelerating voltage there. Sorry, the kinetic energy is not there. Only that much kinetic energy is there which brings it up to the pool. But in the heat case, the energy of the electron is the heat provided to the electron minus the work function of the relevant matter. So there, the energies of electrons are quite different from one another. And here the energies are almost the same because the electrons were pulled and gathered somewhere. And from that pool, you are making the beam to go down. So when the energies of the electrons are almost the same, I am not saying that exactly the same, but are almost the same. This means that a monochromatic beam of electrons can be formed easily. And that is why, secondly, the tip of the field emission gun is very, very thin. And that thinness also restricts the emission of electron to a limited place. So the violent scattering is not there. Here, the SEM cathode tungsten lab 6, Schottky and field emission. And here you can see that the tungsten filament apparent source size is 100 micrometer and lab 6 is 5 micrometer and the Schottky is 100 angstrom and the same less than 100 angstrom, and the same is for the case of field emission gun. Look at the brightness difference. That for the tungsten filament, the brightness is 1 ampere per centimeter square steradian, and for lab 6, it is 20 to 50 ampere. So 50 times, 20 to 50 times more brightness is achieved there. And for the Schottky, it is 100 to 500 times, and for the field emission, it is 100 to 1000 times ampere per centimeter square. Vacuum required. Now look at this: 10 power minus 5 torr, 10 power minus 6 torr, 10 power minus 8 torr, 10 power minus 9 torr. What does this mean? This means that if you are interested in very high quality microscopy, then you need a very high what you call vacuum, and that vacuum demands for very small space. If the space is limited, the area is small, it will be easier to evacuate it. If the area is large, it is difficult to evacuate it. But the quality is not possible for large spaces. So when the space is limited, then the tilting of the sample will be restricted. So in the old days, I used a microscope. It was 200 CX joule, which has now been discarded, but I could tilt the sample 45 degree like this, 45 degree like this, and it almost give you 90 degrees in each direction. The modern microscope, you can't go beyond 30 degree because the space is limited. When you are going for quality, then you will have certain restriction, and that quality is coming from the vacuum, because that filament will not work if the volume is not 10 power minus 9 torrs. So the more refinement, the more restrictions are there. Other factors. Cost of tungsten filament is $15. Lead 6 is $400. And field emission gun is $6,000. Right? So lifetime 100 hours, 1,000 hours, 5 to 8,000 hours. So pay more and get better services. And that was the end of today's lecture. Thank you very much.